all, myself Chiranjeev Sarkar, Vice Chair, Tunnel Association India Young Member Group. So today we are going to start our webinar 41 on geophysical tools for safe tunnels by Dr. Sanjay Rana, founder MD of PARSAN Overseas Pvt Limited. About Dr. Rana. Dr. Rana is the founder director of PARSAN Overseas Pvt Limited. He passed out from IIT Roorkee in 1990 as a gold medalist. He started his career in state government and then central government Department of Atomic Engineering for the initial 5 years. Since 1995, he has been working tirelessly towards the growth of geophysical industry in the country, exploring new and unique application areas in various fields like hydropower, oil and gas, mining, infrastructure, etc. He has carried out a geophysical investigation more than 1,500 projects in India and abroad. He has been instrumental bearing various technologies in the India, including ground penetration radar, high resolution tomography, integrated dam safety investigation, and the passive seismic tomography. So it's over to you, Dr. Rana. Uh, Even I will share. I want to share one of my information. In 2015, I was very lucky to have one training on geophysical investigation under Sanjay Rana sir. That was my first step towards this sector actually. So it's very nice to sir to have you in our webinar sessions from your busy schedule, sir. Sir, it's over to you. You can start, sir.
Thank you so much. Thank you for the generous introduction. And it's always a pleasure to interact with you and see your enthusiasm. I hope my audio is clear. Everyone can hear
Yes,
me.
sir. I would request all
Yeah.
others to mute your mic. Even I am also going to mute my mic after this call. And please switch off your camera. So there should not be any interruption during presentation. So after this presentation, there will be a question answer session. So we request all to raise your hands so we can take question one by one. And you can text your question in chat box also. So please mute your mic for next 30-40 minutes and then please off your camera also. Sir, Sanjay sir, you are audible. You can start.
And you are able to see my screen on your.
Yes, sir. Yes, sir.
All right. In case there is any problem, Mr. Chiranjeev Sarkar, you just unmute yourself and let me know if the screen is not
Sure, sure,
moving or some
sure,
issues. Okay.
sure. And we have
All
already
right.
started this session on recording session also. So people who have missed today's session, they can check it from our recording version also. Okay, sir.
Perfect. Perfect. So, a very good evening, everyone, and thank you, especially to Mr. Chiranjeev Sarkar for inviting me for this session. It's always a pleasure to interact with, especially the young members. You are the future, and you are going to take this entire thing forward in the country and the world. So, yeah, great. Thank you very much for joining. Although I don't know, like it's not a great time. Like after a hard day's work, 7:30 joining a webinar, it's difficult. So I'll try to keep it simple, not go into too much of theoretical and all that. And as a topic, you already know, we are going to talk about geophysics for safe tunnels and underground space development. So I represent PARSAN. PARSAN is a company which is in geophysics. I'll not go too much in detail of introduction and all, but we have offices in Delhi, Kolkata, Jammu and Bhopal. That's our Indian offices. Then we have offices, our own offices in Bahrain, Saudi Arabia, and Singapore. And right now we are working in more than 14 countries around the world. I have been introduced very liberally by Mr. Sarkar, so I'll not go in too much of introduction, except for the fact that over the years, I have also created number of guideline documents, and one of them is guidelines for geophysical investigation of tunnels, which has been published by Tunneling Association of India. So if you get a chance, please go through this document, which again covers the entire thing in great detail. All right, so coming to the subject without wasting too much of time. In the very famous words of Shri Visvesvaraya, The engineer's first problem in any design situation is to discover what the problem really is. That is a very, very wise statement to make, that the first problem which we have in any design situation is to understand what the real problem is. When we say real problem, what we mean is how familiar we are with the ground conditions. So to know the ground conditions, we adopt what we call investigations, right? So if we define investigation, it's a methodology of acquiring advanced knowledge of the site condition so that a techno-commercially viable project layout can be developed, right? So we are trying to understand what the problem is to solve the problem. And for doing that, we are doing investigations. We all know that investigations are the critical part of any project. We also know very well that good quality of investigations, good quantity of investigations, and good time allowed for investigation leads to less uncertainties and less costs and claims. So if you look at any project, like if the project is having good investigation data available, chances are that project will be completed almost in time, project will not have cost claims and cost overruns, etc., etc. But the problem is that when we are talking of a project like tunnel, it is very different from other engineering structures. See, other engineering structures, when we talk about, let's say you are building a bridge. A bridge is having, let's say, 10 piers, and you do some investigation at the pier location, and you are reasonably comfortable with the data which you are getting, because that's where your maximum load bearing structure is going to be. Whereas when we are talking of tunnel, in tunnel we are excavating from one end to the other, millimeter by millimeter, centimeter by centimeter, meter by meter, right? It's a continuous excavation. So any kind of an anomalous zone which comes in this particular path can actually create a challenge. Now, this is from a paper by Parker in 1996. It was in International Tunneling Association. He says even comprehensive exploration program recovers a relatively minuscule drill core volume, that is less than 0.0005% of the future excavated volume of the tunnel. When we say even a comprehensive exploration program, we are talking of an exploration program where we are spending, let's say, 5 to 7% of the project cost. In India, we all know that the project cost which we spend is around 0.75% on an average. So in the case of India, it will, even you can add one more zero to this, it will become 0.0005% of the future excavated volume of the tunnel. So this is the kind of information based on which we are doing the design. So I hope we can appreciate that we are making design with very less information. So whatever decisions we take based on such small information, we definitely can't be called a smart decision maker. So we have a lot of assumptions and very, very small amount of data. I'll give you an example of this. As engineers, you should never assume or guess. You should always measure or calculate. First example is, let's say we wrap a rope around the earth. So as you can see, we have, I'll just take a laser pointer from here, or rather pen, I'll take it. We have wrapped this rope around the earth, right? So this is earth and we have wrapped the rope around it. Okay, now my question is, if we increase length of the rope by 6 meters, how far above the earth's surface will the rope be? So I just increase the length of rope by 6 meters. So how high now it will be from the earth's surface? What will be this height? This particular height, what will it be? Any guesses? You can unmute and quickly give me your guess. You know, the Earth radius is very high. We are talking of 6,400 kilometers. We are just increasing the length by 6 meters. So what is your estimate? How much will this height change if we just increase by 6 meters?
On 1 mm?
1 mm. Okay. Any other guesses? Quickly unmute it and tell. Let me have a couple of guesses at least. 1 mm is the first guess. Any other guess? Yeah, no one is brave to make another guess. All right.
Nothing will change.
Sorry?
Nothing will change, I think.
Nothing will change, I think. Yeah. Yeah, that's what common sense says, isn't it? That Earth is so huge and we are just changing 6 meters. But now go back and do this calculation. Okay, go back and do this calculation. It's very simple to do. The circumference is 2 pi r. You know the r, and now we are increasing the r by just 6, this 2 pi r plus 6 meters, and just see how much is the r going to change. It's 0.955 or almost 1 meter. Sounds unbelievable, right? Right? Do this
Yes, sir.
Yes.
calculation. Do this calculation. Please do this calculation. Okay. That is what we say as engineers. Do not assume or guess. Always measure or calculate. Okay. Please do this calculation. It will change by 1 meter. Amazing. Next question. If I fold a paper from middle and then fold it again, say 50 times. I hope it's simple to understand. I don't have a paper right now, but let's say this is a paper, right? So I take this A4 size paper and I fold it once. This is one fold. And then I fold it again. This is second fold and the third fold. Like this, I keep folding this paper again and again, say 50 times. What do you think would be approximate thickness of my paper bundle? Any guesses?
It will reach beyond atmosphere. Nearly.
Okay. Any other guesses? So thankfully, this time I got the correct answer. Okay. If we take the paper thickness of 0.1 mm, just 0.1 mm, we are going to have a thickness of 0.1 into 2 to the power 50 mm, which is this much of meters. This much of meters. Okay. Which is many times greater even the distance from Earth to Moon. So again, generally, when we take a guess on this, we say, okay, it will be like 1 meter, 2 meters, something like this. Don't assume or guess, measure or calculate. That's what we are supposed to do as engineers. So be a smart decision maker, not a blind decision maker. Now, whenever we are working on projects, underground projects, we always come across a concept of geological surprise. So we come through an aquifer zone, we say that we came across a geological surprise. We come across a shear zone, we say we came across a geological surprise. Why the project which was supposed to be completed in 5 years has not been completed even in 10 years? We came across a geological surprise. Why project which was supposed to be 100 crores has gone to 200 crores? We came across geological surprise, right? So a geological surprise is a very common thing to hear in our engineering world. But the fact is that expertise and engineering solutions are available for dealing with almost any ground condition. So if, for example, you are doing tunneling and you know that you're going to come across a shear zone, no problem. Like you pre-grout it, you consolidate it, and then you go through that zone, provided you know that such a zone exists. So the problem most of the time is meeting the unexpected or uncertainty of the ground condition. I call it that a geological surprise is nothing but a condition which you encountered because you did not anticipate it since you did not investigate it, right? That's what is a geological surprise. So the next question is how much investigation should we do? Like as we say that we are having a tunnel right now, we are maybe doing drill holes every 200 meters, every 500 meters. So based on all this discussion, what should we do? We should start doing it every 1 meter, every 5 meters? That's what we say. Can we turn the ground into Swiss cheese? Well, it's not economically feasible. It is not economically viable. It's not technically feasible. You can't convert the ground to Swiss cheese. So what is the solution? And that solution comes in the form of geophysical investigations. So geophysical investigations for the uninitiated who have not had any earlier exposure to geophysical investigation, I always like to correlate it with this medical science. So in medical science, you have, let's say, X-ray, ultrasound, MRI, CT scan, etc., etc. So what we are doing here is we are sending different kind of rays and waves inside the human body, trying to create an image of what is inside, right? We are not doing any invasion. We are not cutting the human body. We are just sending different kind of rays and waves and trying to find out what is inside. Similar thing we are doing in the field of geophysics. That is, by sending different kind of rays and waves or measuring naturally occurring field like magnetic field or gravity field, we are trying to find out what's inside the earth. So for example, this is a, this is a shear zone in a otherwise good bedrock. Here are two pipes which are buried in the ground, and these are different road layers. Here again, this is the bedrock interface, and on top of that, this is the top overburden. This is all weathered rock, etc., etc. So here the philosophy is the same, that we are not doing any drilling or anything, but without doing drilling, we are trying to find out what's in the subsurface. Our job is more challenging for two reasons. First of all, human body is very well known. For example, you see these joints here, right? Now we know that these joints do exist in the body naturally, right? So these will not be interpreted as fractures. But if there was one more here, that would have been interpreted as fracture. So human body is very well defined, very well known. So it's much easier to interpret the medical data. On the other hand, Earth is not at all well defined. It changes every tens of meters, forget about hundreds of meters, right? So data interpretation is much more challenging. Secondly, human body is available for inspection in 360 degree. Now this person goes inside the tunnel, transmitters and receivers are there all over, almost in 360 degree. And you are able to create a very good image of the what's inside. In case of Earth, unfortunately, that's not the case. We are doing all the measurements from the surface, and that's why our challenge is furthermore. But still, this is the best comparison to start understanding what geophysics is. So geophysics, like in a very, very simple term, if I have to tell to maybe a boy or a girl going in 5th standard, 6th standard, I'll say we do X-ray, MRI, ultrasound of Earth, just like you do X-ray, MRI, ultrasound of human body, right? So that's the simplest way. So the next question is, why it's so important? Why it's so important is, again, go back to the medical example, low cost. So the difference between X-ray and surgery, so it's very low cost. Rapid coverage. These days, hundreds and thousands of kilometers can be covered in a single day if we are talking of airborne geophysics. Most important, continuous information. This is one of the most important benefit where it comes in. For example, look at this diagram here. There is a void here. There is a limestone pinnacle here. There are few anthropological features here. Now, what are the chances that you'll be able to detect all these features only by doing drilling? So you do a drilling here, do a drill here, do a drill here, do a drill here. And chances are that you will not be able to detect of any of these features. Chances of these features being detected are in 1 in 1,000 or 1 in million, depending on what is the size of the objects and what is the spacing between the drill holes. On the other hand, geophysics provides you continuous information. So if there is any feature, even if it's a small feature, you are able to find out continuously. So especially for projects like tunnels, where you are doing excavation inch by inch and millimeter by millimeter, even a small shear zone can create a problem, which can be missed completely if you are depending only on drilling data. So this is continuous information is one of the biggest advantage. Then optimization of drill holes. Remember this part very well. We never say that geophysics replaces drill holes. You see, in geophysics, we are measuring the physical property. It can be resistivity, it can be seismic velocity, etc., etc. But there are so many properties which only can be measured on laboratory samples, right? So you need drilling for sure. It does not replace drilling, but it optimizes. That is, rather than doing drilling every 100 meters or 200 meters or 500 meters and still having a chance of missing your objects of interest, if you do a good geophysical campaign, after that you only need to drill where you need more information about your anomalies. So you don't need to drill everywhere. And of course, then it is minimization of surprises because you have continuous information. So surprises are minimized. And it's always good to have it in early stage application for better planning and smooth execution. Even today, like I'm talking about these techniques since 1995, even today, most of the time, they call you as firefighting stage, at the firefighting stage. Something has gone wrong and then you get a call. Can you come and do something? It is best applied in the early stage. Okay. Now coming to, I will only cover maybe 4 to 5 different techniques in this presentation. Obviously, like idea is not to educate you on geophysics, but to tell you what different techniques can give you at different stages, right? So when we talk about tunnel and underground project site investigation, first thing and most important thing is to understand where geophysics fits in. Because whenever we talk about a technology, sometimes there are few practitioners who talk about a technology like this is the end of it. You know, everything can be achieved by it. That's not true. Geophysics fits at a particular place. So right sequence of investigation starts with study of available geological maps, satellite images, any background data that is available, good engineering geological mapping, and after that comes geophysical investigation. So it comes after geological mapping and before drilling. Unfortunately, today what is happening, after geological mapping, we are directly going for drilling. This is the biggest mistake we are making. So what we ultimately do is that we plan the drilling campaign. Okay, that in this particular stretch, we will do drilling, let's say at this spacing. At this spacing, we will do the drilling, and that's how we go forward. What if something is happening here? What if something is happening here? What if something is happening here? You will not know about this, right? Whereas if you do geophysical investigation first, you can optimize your drilling, and then you can do drilling exactly where it is required for more information of anomalies. And then of course comes hydrogeological studies and seismicity studies, etc., etc. So this is very important to understand where does it fit in. It fits before drilling and after your geological mapping. Now, I have divided this whole thing into 3 parts, right? First is the planning stage. Planning stage is that you know that you have to connect, let's say, point A to point B. So in your, you have this point A and you have this point B, and you have to connect these points through a tunnel. Now, there can be various routes which can be taken. Okay, so tunnel routes can be different. So, what is the alignment you are taking? It will depend on what geology you are encountering. Presently, it is being done based on geological maps or topo data or topo sheets which are available. There is much better way of doing that, and that's what we say planning stage use of geophysics. First is heliborne time domain electromagnetic. So in this, what we do is, okay. So I just wanted to confirm, Mr. Chiranjeev Sarkar, while this video was playing, were you able to get the sound also, or there was no sound?
No, So there was no sound actually.
Perfect. So next time I'll remember that. No, anyway, it was just music, so no sound was necessary. So now what's happening in this is that we are getting continuous data. Okay. So for example, you are taking a tunnel which is 10 kilometers long. So instead of only investigating this 10 kilometer, you can take a strip of, let's say, 500 meters width, 10 kilometer long, and investigate this entire area. The advantage is that now you have practically a 3D information available to you, by which you can find out which is the best alignment to take my tunnel. So that's the first thing. Secondly, when you are working in Himalayas with thick vegetation, etc., etc., accessibility is an issue. Even if you want to do a great geological mapping, your geologist cannot even access the place. Even if you, let's say, drop him by a helicopter, right? No one will do that because the guy, how he'll survive. But let's say you do that, because of thick vegetation, the outcrops are not available, right? So how he is going to do any geological mapping? In all these cases, since this is working on the principle of electromagnetics, which is not affected by vegetation, you are able to get good data of the subsurface, something like this. So this is one example. The depth of investigation can be anything between 600 to 800 meters, depending on various parameters, that is ground conductivity, etc., etc. But this is generally the depth with dual moment tensor which is being achieved. And here is the conductivity. So high conductivity basically means the strata which is weak, having high moisture. Low conductivity means good strata. Now you have got this data. This is the terrain. Now you have got this data, and let's say your tunnel was going at 400 RL. So you can see this. Let's say this was your tunnel. This was your tunnel grade. Okay, right. Don't it is supposed to be absolutely straight. So if it deviates a bit, it's because I'm not sitting on a table right now. Now, here you can see that as you are going, you know that you are going to meet with an unfavorable condition here, and then you are going to meet unfavorable condition here. And in this particular zone, you are going to meet unfavorable condition. Now you're already ready, and a small, very small zone here also, okay, going to meet a very small unfavorable zone. Now you are ready where you will get unfavorable conditions. So there is no surprise for you in store, okay. And this data further can be investigated more in detail by ground geophysics now, or even drilling can be planned for this. So once you have got this data, then you can plan drilling if you want to investigate further. But this is a great starting point. Okay. Second great starting point is passive seismic tomography. The first one, this Heliborn time domain electromagnetic, already has been used in India in couple of projects. Passive seismic tomography still has not been used in any project. It is also very promising. In this, what we do is we put number of 3-component receivers over the surface under which we need the information. And then we are listening to these micro earthquakes which are coming all the time, and especially in Himalayas, there are plenty of these micro earthquakes, and record the P wave and S wave travel times through this these sensors. Okay, we have used this in India, but that is for oil and gas exploration, not for tunneling project. We have done it for ONGC, we have done it for Oil India Limited, and very, very good results. Once you do this, this is a typical P wave velocity model which you get. Okay, these are P wave, and look at the depth here, because sometimes people say that our tunnel might be going at 3 kilometers, maximum overburden can be 2 kilometers. Here, depth is not a limitation. The Assam and Arunachal projects which we have done, Tripura projects we have done, we have gone up to 20 kilometers of depth. Even this section has a depth of 2 kilometers, right? You can see this is 1.2, this is minus 1.2. So basically 2.4 kilometers. Again, if your tunnel was going, let's say at this level, right? So you know that in this particular zone, you are going to have issues, you're going to have problems. The model which comes from PST is a coarse model. So obviously, once you have done PST, you have got a good idea of the entire area, and then you can follow it up by surface geophysical methods or again by drilling. Okay, but this is again a very good method to be applied, which gives you a 3D idea of the subsurface. Then comes seismic refraction tomography. Seismic refraction tomography again is working on the principle of refraction. That is, when we are having seismic waves being initiated by a short point, they propagate in the subsurface. As per the Snell's law, sin I upon sin R is V1 upon V2. So V and V is the velocity. So if V2 is the greater than V1, R will be greater than I, so it will get away from the normal. At one particular angle, it is 90°, and then these head waves comes as per the Huygens principle, not going too much in theory. The whole idea is that this gives you P wave velocity of the subsurface. It can be done in land, it can be done across water body. So this is across water body, okay? Ultimately, you can see the usefulness of the whole thing. This is one project in which few drill holes were available, based on which this geological model was developed. This was the tunnel alignment. You can see the tunnel alignment here. As per this geological model developed, right from here to here, no surprises were envisaged. Only problem was somewhere here. But when seismic refraction tomography was conducted, you can see very clearly that this is going to be a bad zone, and this is going to be a bad zone, and this is going to be a bad zone, apart from these parts. So now you will not encounter these as surprises, because you already know what lies ahead of you. This also can detect very small zones. So this is just 7 to 10 meters thick zone, which again chances of detecting it by drilling are 1 in 1,000 or 1 in million. But this also can be detected from P-wave seismic refraction tomography. Another method for investigation of your alignment is electrical raised to T imaging, which is also called electrical raised to T tomography. So the seismic was based on acoustic waves. So we are talking about strength of the material, because P wave velocity is linked to the strength. Sometimes we are interested in moisture content. Okay, so we are looking more in terms of presence of water. That's where the property of resistivity or conductivity has to be used. So electrical resistivity imaging, we are putting number of electrodes on the ground. These days we can put as many as 120. uh, Computer automatically switches between the electrode to create a picture of subsurface, something like this. Okay, so this is a picture of subsurface. Once you have put your electrodes, so it's a high resistivity and this is low resistivity. So it's a resistivity distribution that comes. And this is one example again from a tunnel project where there was a shear zone and number of drill holes were done trying to find out about the shear zone. And this is one line of resistivity survey. It's some 400 plus 45 meters. This is the depth scale. So it is 1040 to 860. So roughly 200 meters from top point to the bottom point. And the shear zone was detected based on electrical resistivity imaging. This is another very good example. This is a tunnel and then ERI was done. And as you can see, this is a low resistivity zone which was detected here. Another low resistivity zone or medium resistivity zone was detected here. And now based on this, drilling was planned. That is the message I'm trying to give. So this drilling was planned like this. This was planned like this, basically to cross these weak zones and understand what are the properties of these zones. So resistivity profile from section of tunnel, zones of low resistivity are further examined by borehole logging. So drilling and then borehole logging. This is the right way to go about it. These days it is possible to present the results in 3D. So this is a cube which is 60 meters by 300 meters by 60 meter depth. I did it for a cavity mapping in Kota, and this is the cavity. This is all water table, this blue, and this blue is the cavity. And now we can cut this 3D cube in different direction to actually visualize how the cavity is going from one side to the other side. Okay. So this is a very effective method. So this is the cavity which is going all along. Once we cut it from top to bottom, you'll be able to see it like a pipe. So yeah, this is the cavity which was there. Okay. So it's possible to represent data in a very effective way. Next method is refraction microtremor or MASW, which gives you shear wave velocity. MASW also is done for VS30, which is used for earthquake site response and hazard studies. It is working on the dispersion curves of Rayleigh waves, and ultimately you can get this is RAMI result up to 100 meters, and this is bedrock, and this is the very loose zone because of low shear wave velocity. And the last method in this series is seismic tomography or sonic tomography. This is done between boreholes, right? So sonic tomography is done between borehole. Today, what we do is that if we have borehole and we have encountered a formation here and a formation here, we only interpolate between the two. You don't need to do that. And by sending these very intense ray paths between the two, you can get a continuous information between boreholes. And even a feature like fault in this case has been determined based on the tomography. We did this very prestigious project, which is one of the deepest project ever reported in the world for this cavity detection. This was done in Bhutan in Punashangtu 2 project. And the distance between borehole at one point was as high as 115 meters, and depth of borehole was as much as 250 meters. And this was a cavity which was delineated, which was 85 by 60 meters at its biggest point. Very effective method for important high resolution data collection. Then is seismic reflection, which is really used a lot for oil and gas exploration, has never been used in India for tunnel investigation. Whatever case study I have is not from India, it is from Canada. And this is a very strong method which again can give you location of faults and different formations. Depth can be anything. In oil and gas in India, we are using up to 6,000 meters, that is 6 kilometers. Problem is that a lot of logistics are involved in this. You have to use explosive almost every 10-20 meters all along the tunnel alignment, and that makes it very difficult to be used. Otherwise, a good method. There are other methods like MT, GPR, and other methods which I'm not going to discuss because they are very rarely used. So this was one stage. Then comes execution stage. That is when you are doing the tunnel. Again, in execution stage, there are two principal methods which can be used. One is tunnel seismic prediction or TSP. This is a seismic method. So in this, we are sending seismic waves which are getting reflected from the interfaces where there is change in acoustic impedance. So let's say you are going to come across a shear zone, reflection will take place from there. So here we do these small drill holes, explode the small charges, and receive the reflected wave from these receivers. So basically, it is working on the principle of seismic reflection. These waves are going, hitting the target, coming back, and being recorded. And that's how you are getting an idea of what's ahead of you in terms of properties. And as I said, as you come close to this weak zone, you do pre-consolidation, and now you can go ahead of it. So if you know where the problem is, you can solve it. The next method, which now this TSP was based on seismic. Again, every method will have certain limitation, advantages and disadvantages, right? So for example, TSP works very well if the plane, the anomalous plane is perpendicular or only at an angle to it. If it almost becomes parallel to the axis of the tunnel, well, TSP will not detect it because again, the problem is that reflection will not take place. So then there are various other methods, and I always advocate combining methods. Beam is based on electrical. So this is called board tunneling electrical ahead monitoring. So in this, what we are doing is we are making, this is the most efficient and cost effective for TBM ahead prediction because of the automatic, continuous and non-invasive data acquisition processing. In this, we don't have to stop the operation even for a minute. Okay. So we just put the electrode on the tunnel head, one on the shield and one outside. And now stroke by stroke, as the tunnel TBM is moving, we will keep getting the information of what is coming ahead in terms of porosity and in terms of the fluid content. So for example, if there is a cavity coming ahead, you will know 3 times the diameter beforehand. So if the diameter is, let's say, 6.67 meters, 20 meters before, you will know that you are going to hit a cavity. So again, it's a very, very strong method. Both the methods are being used in India. TSP is being used for much longer time. Beam is being used since 2022. Already six installations of Beam are there in India, in Patna and Delhi, and more are likely to happen sure in short time. GPR is another method again which can be used to see ahead of tunneling. Last is QC and maintenance stage. That is, now the tunnel is completed, but you want to do QC. For doing QC, for example, whether lining is good, whether there is a cavity behind the lining, etc., etc., you can use GPR. So this is almost a 3D. So this is a tunnel, you can see. This is a tunnel and GPR has been done. And so this is the seeing inside the tunnel in depth. And wherever you have the anomalous zone or wherever you have the problematic zones, you can detect it. So this is another example. This was done in India only. And you can see how the zones which are there have been mapped. These slices have been prepared. The entire information is available in 3D, like a 3D cube, and you can then cut slices to see at what distance what is happening. Then sometime you can have, you want to find out, where the seepage is coming from. So electrical resistivity imaging can be done from inside the tunnel. So this is one example. Seepage was coming out from here, and the client wanted to know where it is coming from. If you don't do this kind of investigation, you will start grouting here, and no grout will go because this is a very, very compact medium. So your problem will not be solved. Once this investigation is done, we could find out that this is the zone of saturation and the water was taking this particular path and come out here. So now if you need to treat this situation, you have to basically treat this particular zone, not here. And so this is a very, very effective area for doing that. So coming to limitations and reasons of failure, because more often than not, you'll hear that, oh, we used geophysics, but it didn't work. First is inadequate planning and survey design. Most important part in geophysics. I always say it's a 7-step process. First is the planning. You have to sit down, which method will work, what is the problem. Inadequate planning and survey design is the first problem. Wrong tool selection. If you want, strength of the material and you are using electrical resistivity imaging, right? Method lacking desired solution, geology ignored, only single tool used. This is again a very big problem. There are many practitioners who have only one method available with them. For everything, they want to use that. Then technological failure, equipment was not working, and then data processing and interpretation error, which happens when a person is not having enough experience or expertise. So to conclude this, this geophysical methods provides valuable and continuous information for the planning and execution of tunnel and underground projects. In addition to usually applied geological and geotechnical exploration is necessary to achieve accurate and continuous models of the subsurface in short time schedule. To achieve optimum benefit from geophysical investigations, it is necessary to apply these methods after intensive discussion between geologists, engineers, and geophysicists, and at early stage of the project. And then combination of different methods, that is geophysics, geology, and geotechnics, as well as the so-called joint interpretation techniques, will be of essential importance. It ultimately leads to increased safety and decreased risk. So this was my presentation, And this is a small QR code. If you take out your phones, just scan this QR code, and there'll be a small form, I think, where you just have to write your name and your email ID. So within next 10 seconds, you will receive in your mail guideline on geophysical investigation of tunnels and advanced geophysical techniques for rapid subsurface investigation for mega civil projects for free. And this is that guide I talked about. This is a very good guide on geophysical investigation for tunnels. All you have to do it, just take out your phone and scan this QR code, and then just write your name and email ID, and it will come automatically to your email in next 10 seconds of time. Okay. So with this, I conclude my presentation. Thank you very much. Mr. Sarkar, back to you.
Yeah, so now it's time for question answer. So we are requesting all to unmute yourself. You can raise your hand. We can take question one by one. So already, sir, two question we have already received. The first one is the sir, tunneling in the urban area where building exists above the tunnel, where there is no space even for soil investigation along the alignment. Can this survey be adopted?
Yeah, it's a very good question, and it's a very big problem also. When you are tunneling in an area where where the buildings are right over your tunnel alignment, so of course you cannot do anything which comes in terms of geotechnical investigation, and whatever surface geophysical methods I talked about also become inapplicable because you are having buildings there, so you cannot do any surface geophysical method. Now there seismic tomography comes to your rescue. That is, if you're, because in these kind of areas you can do borehole on one side and on the other side. So if the houses are there, in front there is a road and back side there is a service lane. You can do boreholes there, and between these boreholes you can do tomography, which will give you information about what subsurface in that particular area. That is the only thing which you can do in such cases. That is one. Number two, in such cases it is even more important that you use the methods which I talked about, like beam. Okay. So you now, once you are doing the tunneling using TBM, your beam is installed, and stroke by stroke you are getting information that what is coming ahead of you. When I say what is coming ahead of you, it can be a aquifer, like it happened in Kolkata metro case. It can be a metal cage. It can be a foundation kind of a thing, and beam is able to give you that, or cavity. So beam is able to give you that signature. So it becomes very critical to plan these things in such cases. Okay.
So the next question is, uh, sir, how much time required for earthquake wave testing for a tunnel approx 4 km length?
Sorry, 1 minute. I'll just try to read that. Where is this question?
Mr. Dhiraj, that how much
Okay.
time
How much
required
time
for?
required for earthquake wave testing for a tunnel approximate? Well, earthquake wave testing I did not talk about. And there is like, I don't know which method you are talking about. But if you are talking about earthquake response studies, which we said, that is based on MASW, right? So I just clarify your question again. Earthquake wave testing, we never talked about any method like earthquake wave testing, because there is no such method like earthquake wave testing. We talked about, P wave, the seismic refraction, MASW, etc. Just clarify in your next point. Yeah.
Mr. Raghavendra, yeah, you can directly ask your question by unmute yourself.
Yeah, this is Raghavendra here. I think this same question you answered, sir, already just now. In urban areas where a lot of buildings, and we want to do this geo technical investigation by one of your whatever methods. So you said already replied to this, no? It is seismic sonic tomography, no, sir?
Sonic tomography. Yeah, we can call it seismic tomography or sonic tomography. That's right. Yeah.
Yeah, and see, once the tunnel is ready, we can do it from inside the tunnel also.
Once
Correct,
the
no?
tunnel is, yeah, right. Once the
Yeah,
tunnel is ready, you can do
this
it from inside the, yes.
Yeah, the main problem is when tunnel is not ready and we want to know what is this one investigation.
Exactly. That time, the only thing which comes to your rescue is seismic tomography between boreholes,
So
right?
there is no other method, no, sir?
Now, since you can't access the top of the whole thing, there is no other method.
Yeah. Okay,
Okay.
sir. Thank you.
Sir, now that question has come, that can you share some detail about the geophysical investigation role in the Silkwara tunnel case? A little insight about how investigation is conducted in the disaster scenario. I thought that this question definitely will come. Yes, we have a planning to arrange a separate discussion for Silkwara tunnel case definitely in the coming days. But still, we request Sanjay sir to share his experience actually in that regard.
To be very honest, I really wish that I didn't have to conduct any investigation in Silkyara case. That means that Silkyara shouldn't have happened. That's what I said in the beginning, that we should focus on investigation in the initial stage rather than these disasters happening and then try to do the firefighting. Geophysics in Silkyara especially had a very limited role, for the simple reason that once the tunnel collapse has already happened, right, and the entire debris has fallen, and then the hole also was done. When I reached there with the seismic reflection, GPR, ERI, and magnetometer, four different techniques. The Our idea was to find out first the thickness of this material which has fallen, for which we plan to do seismic reflection. But unfortunately, drilling already had started and they didn't want to stop drilling for even 1 minute. So you can't do any seismic work when it's not done. Ultimately, we ended up doing some GPR work there to see through the debris, etc., etc. Most important, what we did was that when the vertical hole was planned from the top, so we did number of investigation on the top of the hillock to make the right location of vertical hole and to see that if it will come across any issues or some water lens and all that. So there were number of methods which were used, and we all were very lucky and happy that people could be rescued safely. Any other question we have?
One more question from Mr. Rahul Sharma. Yeah, you can ask question directly.
Good evening, sir. Rahul Sharma this side. It's again pleasure to listen you one more presentation. Sir, I just have one question that what sort of cost analogy in all the various methods? Because I heard that ERT and SRTs are nowadays very common in most of the underground projects. But still, people are more hesitative regarding these helipad methods, which is very useful in kind of northeastern region. So I just want to know about the cost analogies between the various geophysical methods.
Well, see, electrical and seismic, you already know they are very cheap. For that matter, when I started in 95, the first seismic refraction survey which I did at Jamarkotra mines near Udaipur, I charged some 300 rupees a meter for that work in 95. And today the same thing is done at 200, 250 rupees a meter. And that time salary of a geophysicist or engineer used to be 3,000 rupees. And today the salary cannot be less than 50,000, 60,000 rupees, right? So actually the prices have come down. So, but yes, electrical methods, seismic methods range between 200 to 500 rupees a meter, depending on the terrain and things like this. When it comes to heliborne survey, they are slightly more expensive for the simple reason that helicopter gets involved in that. So most of the cost is of the helicopter, but it's not still very expensive. If we talk about a 10-kilometer tunnel, like what it will cost, let's say 6-7 crores of rupees, which is nothing compared to the cost which we otherwise incur when we get into trouble. So I still believe that geophysical methods are not used because of lack of awareness, number one, lack of practitioners, number two, and yeah, some failures which happen, which discourage people from using that. But otherwise, no one can beat the cost effectiveness and ROI, as we say, return on investment of geophysical method. There is no comparison.
But sir, there isn't a need of ground connection as well, in case of helipad connection. Just like if it in a urban area, just in the case of Mara section. It is a problem because the buildings are so much closer, and if you want to something in TVM tunneling, need this accessibility. So definitely these will be little unworkable if we are trying for the helipod bond methods.
Heliborne is absolutely not even suggested in the urban areas. Heliborne time domain electromagnetic is only and only for virgin areas like Himalayas and all that, where you have this vegetation, etc. We
Right.
never fly over populated area. Once it comes to
Yeah, right.
populated areas, you have to start with surface geophysical. See, there is a big difference also. When you're talking of populated areas, you're talking of urban tunneling. Your urban tunneling is happening at 25, 30 meters, 35 meters maximum, right? We are not going at 100,
Correct,
like
sir.
700, 600 meters overburden. So obviously, we are not even
True.
talking of that. There we are using either surface geophysical methods if possible. Otherwise, things like tomography and ultimately things like beam when actually tunneling is taking place.
Okay. Thank you.
No other question. Everyone seems to be in a hurry to finish it up because it's already 7:30, 8:30. Yeah.
Mhm. Sir, sir, nowadays drone survey is also gaining popularity. So, is there any mix up things like instead of helicopter, drone can be used in the geophysical investigation to reduce the cost? These things, sir.
Very, very good question, actually. If we sometime talk more elaborately on geophysical methods, I always tell about contacting methods and non-contacting methods. Okay. Contacting methods are the one in which we need contact with the ground, like electrical resistivity imaging. You need electrodes in the ground. Seismic refraction, you need geophones in the ground. But there are non-contacting methods like GPR, okay, like electromagnetic, then like magnetometry. All these methods have a great potential to be used by drone. We are already using GPR by drone. I have used it myself to find out tunnels in the border areas, which are used by these terrorists to smuggle arms and things like that. We are working extensively to detect these underground tunnels and very effectively using drone-based GPR. Then drone-based magnetic survey again is very common for mineral exploration. It is already happening in the country. And this time domain electromagnetic, maybe 6 months after this presentation, I'll come and tell you because it has already been successfully tested in one pilot project in Norway uh, using drone instead of helicopter, right? But they are still trying to make the system more robust. So for commercialization, it will take maybe 6 more months. And after that, maybe we'll talk about instead of helicopter, drone-based electromagnetic, which will change the whole thing drastically in terms of ease of doing it, in terms of the cost and everything. So very good question, Mr. Sarkar. Very soon it will happen. It will happen. I hope so.
Sir, in your presentation, we have seen that you have also recommended that geophysical tests should come much earlier than the geotechnical investigation and the mapping things. Generally, what's happened in my experience, I also seen that we ask geophysician for their confirmatory, but things not it should become earlier. So, is there any specification or is there any update that some contractual or any technical specification in the railways, metros, and other projects that it should be mentioned in the tender or contract itself that this much of geophysical investigation you have to done earlier your geotechnical investigation. So I think with this practice, these things will change.
Very true. That is what is supposed to happen. Still, it is not there, to be honest. Okay, but there is no point. Again, going back to the same analogy. Let's say you go to a doctor and you have some problem. You have some pain in your stomach, and doctor takes you to operation theater, cuts you open, and then after that he says, okay, now let's take a
Mm.
x-ray or ultrasound also. Now that's stupid, right? So similarly, in terms of investigation, as I said, start with the available geological maps, then you're doing satellite image studies, then you're doing geological mapping, right? After that, you have to do geophysical investigation before drilling. Drilling should be optimized, and the location of drilling should ideally be chosen based on geophysical investigation. Unfortunately, that is not happening as of now, except in few areas like oil and gas. Oil and gas, no well is ever drilled unless geophysical data tells you that this point should be drilled. Reason? Every well costs hundreds of crores of rupees to drill. Okay. In our case, the problem is that drilling is not so expensive. Like one drill means, okay, a few lakhs of rupees. So they do drilling like randomly anywhere they want. But that's not the right approach. The right approach is to do geophysics and then do the drilling.
So matter come to the cost actually.
Yeah, but the cost of, as I always say, the cost of geophysics is negligible. Negligible in the sense that, see, I just give you one example. Uh, as I said, seismic refraction, let's say, is costing 200 rupees a meter. Okay. One line of seismic refraction, let's say, is 115 meters. Okay. 115 into 200. So it is coming to what? Around 20,000 rupees. Okay. The information you are getting is equivalent to doing a borehole every 1 meter for 115 meters. So what is the cost of 115 meter for 115 boreholes of 30 meters? It will go in lakhs of rupees, right? That is the comparison, right? So cost is of geophysics is negligible, provided you plan it correctly. Unfortunately, if you do it after drilling, there is no point of doing it. You already have wasted your money there, you know.
Yeah. Okay, sir. I think there is no question. So, okay, one question from Mr. Yeah, Mr. Dhanwant, you can ask directly.
Yeah, good evening, sir. I am Dayanand here. Hello.
Yeah, please go on. Please ask a question. Yeah.
I am working as chief engineer for Bangalore Metro Rail Corporation. We are doing the tunneling in Bangalore. The beam, whatever you have said, beam application, that appears to be promising one for the tunneling in with tunnel boring machines. So I wanted to know how much time it will take for you to install the instrument, and what is your role during that during the tunneling? Only we have to take the instrument and install it, and we will get the data, or do we have to depend on you full time?
No, you don't have to depend on us. Once, see, the entire panel has been made in a way that it can be interpreted by even an operator. So there is no interpretation involved. It is directly giving you, for example, if you are going to come across a bad zone or something, it is being displayed in the screen. It also, the data can be shared to different places across the country. So it is something where you don't need our role. And we anyway do not sell the equipment. The equipment is given on a monthly rental kind of a thing. Okay. And the data is given to you. You have the access to data till whatever time you want to use the system. It's great. After the system is again it comes back to us. So, but since you would like to have more discussion in that, so my email ID I'll just write in the chat box here, and you please send a mail to me, and then we can take it further with more details.
The instrument will be fixed on the cutter head or inside like the operator chamber or somewhere.
Okay, there are basically three electrodes which are there in beam. One is fixed right behind the cutter head on the stationary part, not on the rotating part. Okay. Second electrode is, that is one cable is connected to the shield of the TBM, and third electrode goes outside in the natural ground. That is how it happens.
That means before actually the TBM starts mining, we have to fix these instruments, electrodes.
Not necessary. You can do it at any time, because as I said, it is not fixed to the front rotating head. So it is fixed to the stationary part, which is behind that, and then the shield, and one is outside. So in any tunnel, any TBM, at any point of time, it can be fixed. It need not be in the beginning.
And you said it has been fixed in Patna and Delhi. So how is the result there? Actually, how the information gathered is good enough?
Yeah, see, this question is answered by the approach of the client itself. So first one system was installed in Patna, and then client asked for another system to be installed there. Similarly, in Delhi, first two systems were installed, and then client asked two more to be installed after seeing the data for around 3 to 4 months of time. So I definitely feel that this conveys a message that the information is very useful.
Can you throw some light on the cost?
That's very difficult for me to be very honest right at this time, because I am not directly looking into it. I have a separate person in my organization. It's Commander Ashutosh Kaushik. He is my CEO. He looks after the proposals. I've just given you my email ID in the chat box. If you can have a look at that, just drop me a mail. I will connect him to you. Okay.
Yeah. Thank you, sir. Thank you.
Thank you.
Yeah, I think there is no such question. So it's already 8:41. So okay. Thank you everyone for attending such amazing session. So